yellow, 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 yellow. Yes, alam ko.
Hey everyone, welcome back and let's write some more neat code today. So today let's solve another graph problem, walls and gates. So we're given an m by n grid where each position could have three possible values. A -1, which represents a wall, aka an obstacle that we're not allowed to visit. We're not allowed to visit these walls. A 0, which identifies a gate, so this is an example of a gate in this case. And the third value is infinity, which basically represents an empty room. And basically for every single empty room, aka every position that's marked as infinity initially, we want to identify what's the nearest gate to that room, and then we want to take the distance from that room to the nearest gate and then replace that infinite value with it. And if it is impossible, basically if an empty position cannot reach a gate in our graph, then basically we're going to leave that position as infinity. So for example, let's take a look at this example. The easiest one over here, right? How far away is this empty room from a gate?
Population
Well,
is
it can go in two
100.
directions. It can go down, which is one position, but it happens to be that there's a closer gate if we go to the right and then we go up that position, right? But be every single position in these. First things first, let's get the dimensions of our grid, so the number of rows and the number of columns. I usually like to do this at the beginning, and we're also going to have a visit set that is going to make sure that we don't visit the same position multiple times, and we're also going to have a queue, which initially let's set to being empty, but we're going to initialize that with the gates first of all, right? So now let's go through every single position and actually initialize our queue, right? And we know we're just going to do that with the gates. So we're going to have to go through the entire grid. So iterating over the entire grid. And even though we're doing this, it's not add it to the visit set because we don't want to have to visit this same position twice. And now we can actually start doing our BFS. So initially the distance is going to be 0 because we're going to be popping the actual gates first of all. So we're going to say while queue is non-empty, we're going to go through every single position in the queue currently, right? Basically this layer of the queue. And so we're going to be popping from the queue. So pop left from this queue, we're going to get the coordinates of the gates that we initially added, right? That's going to be the first layer. The first layer we're going to of the gates. But the reason I'm putting this line here is because after we pop the gate layer, the next layer that we're going to add to our queue is going to be all the rooms that are one distance away. So after this for loop, let's make sure that we remember to increment our distance by 1 every time we complete a full layer of the queue. And so basically for this room, let's just go ahead and add room. We're going to add every single neighbor of this room. And you can see I haven't actually defined that function yet. So let's do that up above once I actually write this out. So basically what I'm doing is going to be adding all 4 adjacent rooms to the queue. And we obviously know that some of these rooms might be out of bounds. Some of them might have already been visited. That's why I'm going to put this in a helper function to basically abstract some of that logic for us. So let's define the function up above over here. So add room, we're just going to pass in a couple coordinates. So basically if this row is less than 0, or if the row is out of bounds, meaning it's too big, meaning it's equal to the number of rows, or the exact same thing for column, if column is less than 0, or column is too big, or if this position, row column, has already been visited, or one last condition, basically if this room is a wall or an obstacle, right? Because remember, not every position in our graph is a empty room. It's possible it could be a obstacle, meaning it's equal to -1. So if any of these above conditions is true, we're going to immediately return because this is an invalid room. So we're not going to actually add it to the queue or the visit set. But if it's not invalid, that's when we can go ahead and say, okay, visit dot add to the hash set and go ahead and queue dot append to the hash set as well. Right, so basically you can see why I'm putting this stuff inside of a helper function, because we don't want to have to call that 4 times. And I don't really want to put a loop in here because I just think it's kind of messy. I'd rather just write it out like this. But so with all of that done, we can see that we have added the rooms. We're making sure to increment the distance every time we complete a layer. And we're basically going through rooms, labeling what's the minimum distance from that room to a gate. Once we're done with that, we don't actually have to return anything because we just have to modify the rooms to the array in place. So this is all the code that we're actually going to have to write. So you can see that this solution